Okay, so consider this elliptic billiard shown in black here, a over b equals 2, and the family of 5 periodic orbits, which I'm going to animate. So here's a family of 5 periodic orbits. You can see here that its perimeter is constant at 9.1887, though its area, A, is not constant over the family. Okay, now I'm also showing a very interesting centroid called the Steiner curvature centroid, which is the weighted average of the vertices weighted by sine of 2 theta, where theta are the internal angles at each vertex. So this centroid has very interesting properties, one of them being that uh, if you draw the paddle polygon of this blue polygon with respect to it, so let's do that. This is out of all possible points, this K on the plane, this is the one with the least area. Okay, so Steiner showed this in papers that he wrote in 1825 and 1838. So here am I with this K. I'm dropping perpendiculars to each one of the sides of my original polygon, and the resulting paddle polygon has minimal area out of all possible K's on the plane. So let's just observe this guy here for a second. Over the family, you can see that it is not stationary. Actually, when n is an even number, this K is stationary at the center of the billiard, but when n is odd, it actually moves around. It actually moves around on an ellipse, which I'm going to show you guys in a few minutes. All right, now the really cool result here is that if you compute the area of this dashed paddle Steiner polygon of minimum area, displayed here as A sub k, the ratio A over A sub k is invariant over the family. There it is, 1.6181 for this particular A over B equals 2. All right, now let's now draw. I'm going to remove the paddle polygon from the screen. I'm going to draw the outer polygon. This is this green polygon here, whose sides are tangent to the ellipse at the vertices of the 5 periodic. So let's observe this derived polygon and its K prime curvature centroid, which is not congruent with K, and it's also moving around along an ellipse. Let's draw the paddle polygon of both. So let's stop this. Here's paddle polygon. Let me remove the orbit for a second. Let's just look at the actual outer polygon to the 5 periodic and the paddle polygon of this outer polygon with respect to its curvature centroid, represented here as K prime. A prime represents the area of the outer polygon, AK prime the area of this extremal minimum area paddle polygon, and this is the ratio of the two areas. Again, we get this beautiful phenomenon whereby the ratio is invariant, with K prime moving along its own ellipse. Finally, let's look at the inner polygon. What's the inner polygon? So let's put the 5 periodic back on the screen here. The inner polygon has vertices where the 5 periodic is tangent to the confocal caustic shown here in brown. So these 5 touch points here define what we call the inner polygon. It too has its centroid, its curvature centroid, and its own paddle polygon. Let's turn off the 5 periodic here, and let's examine this. So there's its minimal area Steiner paddle polygon with respect to K prime prime. Again, we got the same phenomenon. While the area of the inner polygon is varying, as is that of its Steiner minimum area paddle polygon, that ratio is invariant. Now, I'm showing you guys here invariance in terms of numerics, but up to a machine precision, these numbers don't vary, and we just ultimately need to prove these things more rigorously. So let's examine now a very interesting phenomenon, the loci of these three guys. So I'm going to place them all on the screen. I'm going to remove the paddle polygons for a second, and I'm just going to display the three Steiner curvature centroids, which he calls Krümmungs or Krümmungs Schwerpunkte. So centroids of curvature, Krümmungsschwerpunkte. So you can see here that the three Krümmungsschwerpunkte are moving, in fact, along independent ellipses. They are not similar in any way to the billiard or the caustic, and these three ellipses are not similar to each other in terms of their A's over B's being different, but they are ellipses numerically. So again, we need to prove that these guys are true ellipses more rigorously. But again, the pleasant phenomenon here is that the ratio of each one of the polygons, orbit, outer, and inner, by the respective Steiner extreme or minimum area petal polygons are invariant over the phi periodic family. And I've repeated this simulation for ON. When n is even, the three curvature centroids are located in the center. You still get this invariance, but centers are stationary. And for other n's, such as n equals 3, n equals 7, all the other odd n's, you get the exact same invariance. Okay, guys, so hope you've enjoyed this phenomenon. Thank you very much. Thanks for watching.